Let us look at proposition number 29 of book 10 of Euclid's Elements. Now, in this proposition, actually, we have two lemma. So let's look at the first one, then we will look at the second one, and then we will look at the proposition. The first lemma says to find two square numbers such that their sum is also square. And I'm sure you are familiar with this. A square plus B square equal to C square, right? Sum of two squares is equal to a third number square. Let's see how to find such numbers. You are more familiar with this being called as a Pythagorean triplets. Okay, let's see how to find that. Set out AB and BC. And here AB and BC are either both even or both odd. The idea of having something like this is that the remainder of AB minus BC, that is AC, will be even. If AB and BC both are even, and if we subtract them, we will get a even remainder. If they are both odd, again we will get a even remainder. Now we bisect AC at D. So D is the midpoint of AC. Let AB and BC be similar plane numbers or square numbers which are also similar plane numbers. Actually, this again is a requirement. So AB and BC are similar plane numbers or squares which are also similar plane. I'm sure you remember what are similar plane numbers. Plane numbers are product of two numbers. Yes. So now we have to go back to a very old proposition which we saw. That if this is the setup, then AB by BC plus CD square is equal to BD square. This is a proposition in book 2. Okay, so based on that and based on this setup, we can write it like this. Again, AB by BC is a square number. How? We have already seen in one of our previous propositions that if two similar plane numbers we have, then their product is a square number. So AB by BC is a square number. So which means two square numbers have been found, AB by BC and CD square, whose sum is a square, that is BD square. So AB by BC is a square number, CD square is a square number, and BD square is a square. So a square number plus square number is equal to a square number. So which is what the purpose of this lemma is. Now, based on this, we can also say BD square minus CD square is equal to AB by BC, which is also a square. When AB and BC are similar plane numbers, and same thing, BD square minus CD square is equal to AB times BC, where AB by BC is not a square when AB and BC are not similar plane numbers. So here when we set up these numbers, AB and BC, we have to make sure that they are both even, both odd, and they are similar plane numbers or square numbers which are also similar plane. That is lemma 1. Now let's look at lemma 2. It says to find two square numbers such that their sum is not a square. Okay, let's see how we can do that. Set out AB and BC similar plane numbers. Remember, plane numbers are product of two numbers. So AB is a product of two numbers and BC is a product of two numbers. And similar basically means that those two numbers are in proportion. AB and BC are either both even or both odd. Why? Because when we subtract these two, AB minus BC, that is AC, that should be even. So if both are even, we subtract, we get an even number. If both are odd, we subtract, we get an even number. Okay. Now we bisect AC at D. Now, since D bisects AC, we know AB by BC plus CD square is equal to BD square. This is a proposition in book 2. So this was, the steps were very similar to lemma 1. Now, subtract the unit DE. Now, why are we doing that? Because we want to get a number which is not a square. And in the previous lemma, we saw that we had sum of two squares as BD square. So we subtract 1 or unit. Now, which means AB by BC plus CE square. Instead of CD square, CE square will be less than BD square. Why? Because CE is less than CD. So CE is less than CD. So that means its square is less than this square. So the left-hand quantity will be lesser here. So since it was equal to BD square, this will become less than BD square. Assuming AB by BC plus CE square is a square. The sum of these two is a square. Let's assume that. Means AB by BC plus CE square is going to be less than or equal to BE square. Because remember, we have subtracted a unit here. It can't be greater than BE square. Why? Because then BE will cut into this unit, which is not allowed. Okay, so it has to be equal to BE or less than BE square. Let's take the first case where it is equal to BE square. AB by BC plus CE square equal to BE square. And remember, AB by BC is a square. If we take up that particular case, BE we know is a unit. Now let's have AG equal to 2 times D. So AG is equal to 2 times D. So AC is equal to 2 times AD because D is the midpoint. AG is equal to 2 times DE. And if you work it out, you will notice that GC is 2 times EC. So which means for GC, E is the mid. So we have GC is bisected by E. So which means we can apply the same proposition from book 2. GB by BC plus CE square is equal to BE square. So that particular proposition from book 2 is being applied here and here. AB by BC plus CE square is equal to GB by BC plus CE square. So right hand side is here. We have arrived at this, but we started off with AB by BC plus CE square equal to BE square. So these two become equal. If we subtract out CE square from both the sides, we end up with AB by BC is equal to GB by BC. So again, BC is common to both the sides. So if we ignore that, we end up with, let me write the steps. We end up with AB is equal to GB, which is not possible. AB is not equal to GB. Why? Because remember, we subtracted 2 times D from AB. So GB is smaller than AB. It can't be equal. So since it is not possible, that means AB by BC plus CE square is equal to BE square is not possible. Now let's take the second case. That AB by BC plus CE square is less than BE square. We saw for equal to, now we are looking at less than. Now, let's take a point F, less than BE square. So it has to be on this side. So we again subtract. So let AB by BC plus CE square equal to BF square, because we want it to be less than BE square. So we are saying let it be BF square. Let AH is equal to 2 times DF, which means CH is bisected at F, which means again we can apply that book 2 proposition. HB by BC plus FC square is equal to BF square. And we also have other one. AB by BC plus CE square is equal to BF square. So both are BF square. So we can equate them, which is again not possible. Why? Because if you look at this, FC square and CE square, FC square and CE square, FC square is going to be less than CE square because FC is less than CE. So just because of this itself, we can say that they will not be equal. So it is not. And in any case, we have said that it can't be greater also. Why? Because then we will be cutting into the unit. So AB by BC plus CE square is not equal to a square. So we have found two square numbers such that their sum is not a square. That is lemma 2. Let's look at the proposition. The proposition says to find two rational straight lines commensurable in square only such that the square on the greater is greater than the square on the less by the square on a straight line commensurable in length with the greater. So let's see what this means. Set out any rational straight line. So let's set up a rational straight line. Set out two square numbers CD and DE such that the difference CE is not square. Okay, let's do that. So we have CD, which is a square number. DE is also a square number, but CE is not a square number. Describe the semicircle AFB on AB. So let's first draw the semicircle. Now on this semicircle, we have to find a point F so that we can form a triangle. And that point has to pass through the semicircle. Now, this should be such that CD is to CE. CD, which is a square number, is to CE, which is not a square number, is equal to AB square is to AF square. Let's do that. That is our point F. And this point satisfies this condition. CD is to CE is equal to AB square is to AF square. And we have joined FB. AB square is to AF square is equal to number is to number. Number is to number. That means since it has a ratio that a number has to a number, AB square is commensurable with AF square. And AB square is rational. So AF square is also rational, which means AF is rational. CD is to CE is not equal to a number square is to number square, because remember CD is a square number but CE is not a square number. So it doesn't have a number square is to number square ratio. So therefore AB square is to AF square is also not equal to a number square is to number square. That means AB and AF are incommensurable in length. AB and AF are incommensurable in length. AB and AF are commensurable in square only. Yes, so they are not commensurable in length, but they are commensurable in square only. So in conversion, we take this proportion and we do a what is called as converted. Basically, what we do is we take CD is to CE, but instead of CE, we take the excess. So CD is to D is equal to AB square is to BF square. CD is to D is equal to A number square is to number square ratio. Because now here we are not talking of CE, we are talking of DE. So CD is to DE has a number square is to number square ratio. Remember, CD is a square number and DE also is a square number, which means AB square is to BF square is also having the ratio that a number square has to a number square. Because CD is to DE has that, AB square is to BF square will also have that. That means AB is commensurable in length with BF. AB square is equal to AF square plus BF square. This we know, Pythagoras theorem. D is a right angle subtended by the diameter. So which means AB square is greater than AF square by BF square, commensurable with AB. So the required rational straight lines are AB and AF. So here if you remember, AB is any straight line, rational straight line we took, and AF is the one which we have evaluated using these square numbers. That is proposition number 29 of book 10 of Euclid's Elements. Again, let me remind you, there is a link to a PDF book which describes all these propositions in detail. Please feel free to download it, refer to it, and if you think somebody else can also benefit from it, please do share. That's it for now.